Hey everybody, welcome to the AP chemistry stream for today, day 7 of our wonderful quarantine. Hi Isaac. How is everybody doing? Are we going crazy yet? Governor just announced that we've got another month of this, so May 4th, everybody. Yay. Let's see. Whoa. A bunch of chat just came in all at once. Okay, so Haley is like all business. 79, 93, 95. Isaac also wants 95. Okay, goodness, I'll do number 95. You guys need to chill out. Notice on our time, we have this 10 to 10:05 as welcome. Isabel, I'm grateful that you decided to give up playing Animal Crossing to come play. Let's see, 79, 93. Make notes of those. Oh, I'm proud. Could knock an English master Chinese somewhere. Good job, Isaac. I just got an email. What was that? Oh my gosh. Why do you teachers suck? Everybody else is emailing me all the time. They're just like, hey, I have this stupid thing to say. I'm going to hit reply all. No, sorry. Some of them are just obnoxious. Seriously. I don't know. It's just people have like this one-on-one conversation, but instead of just putting it as an individual email, they decide to include the entire faculty. Isaac, that's David. He graduated a couple years ago. He's just going to help me out with some of the Twitch stuff. I'm glad Haley and Anna are playing Minecraft together. It's always good to play some Minecraft. Well, I guess I'll look at 95. Oh, no, definitely threw that away. Yeah, no, I've never played Minecraft. You're right. Never played Minecraft. I'm sure I'll play it at some point when my son gets older and we'll probably be interested in it, but I personally have never played. Oh, yeah, that one. Okay. Yeah, I'm tired. Okay. Stream it, you coward, with the 2 T's. Yeah, no, I'll probably play at some point. But I've got other things to do. Oh my gosh. Okay, yeah, no, I've got other video games I want to play, like League and Satisfactory and other things. So, yeah. Okay. My factory is epic. I should do a little showing of my factory. I'm glad. Yeah, I've got I just finished my full supercomputer factory and my full turbo motor factory. So I have a giant factory that produces supercomputers and turbo motors all at maximum capacity. But I'm busy today. Maybe I'll stream it tomorrow night or something. I've got the esports team has their game against Provo today. Good, Isabel. Thank you. Yeah, so Brighton plays Provo today in League of Legends, so I'll probably stream that this afternoon. And then tonight I have my BYU class I have to teach, so I'm busy for today. We know you're a retired Minecraft pro, Mikey. You don't need to flex that hard on us. All right, let's dive into number 95. So number 95. 95 tells us that H2O solid goes to H2O liquid. I do my college class as well. Yeah, I'm doing pretty much a very similar thing for my college class. Maybe crafting test. All right, so water is a solid, water liquid. They tell us that the delta H here is 333 joules per gram, which is annoying because it's not in the right units at all. Okay. So what we have to do to answer part A, we have to find the delta H naught. And so to do that, we just change the units. So for part A, remember that delta H naught is the units of kilojoules per mole. So we want to know how many kilojoules are in 1 mole of water. We know that 1 mole is 18 grams. 1 gram is 333 joules. And 1,000 joules is a kilojoule. So the first step is really just changing this joules per gram into joules per mole, or kilojoules per mole, to get the delta H naught. So 18 times 333 divided by 1,000 gives us basically 6. Right? So we know that the delta H naught for the reaction is 6.0 kilojoules per mole, right? Positive because we're melting the ice, endothermic, right? It's going to require energy. Okay. Letter B says to calculate delta G at 0 degrees C. Now, this one's actually kind of funny because what do we know about the temperature, the normal freezing point of ice, the normal melting point of ice? Yeah, it's 0. And so what should delta G be at 0? It should be 0. Yeah, there's a delta G at 0 is 0. Right? The reason why delta G naught is going to be 0 at 0 degrees Celsius is because this reaction achieves an equilibrium at 0 degrees Celsius, right? The melting point, the freezing point, is the temperature that solid can change to liquid and liquid can change to solid. And so that's why at 0, delta G is 0. So letter C then asks to calculate delta S. Now there's 2 ways we could calculate delta S. We could look up S in the chart, or we could use this information that we have already given to us. Because we know that delta G naught equals delta H naught minus T delta S naught, right? And we already know 3 out of the 4. And so we can plug in 0, 6.0, 273 Kelvin, and then we can solve for delta S. Right? We subtract 6, we divide by negative 273. Delta S naught turns out to be whatever 6 divided by 273 is. 0.0220 kilojoules per mole Kelvin. Or we could say 22 joules per mole Kelvin. Yeah, you can. So you can treat it as an equilibrium. And we know that at 0 degrees C, it's at a perfect equilibrium. All right, letter D then asks delta G at negative 20. So now we just plug in our new terms, right? So now that we know S and we know H, we can find delta G. So delta G naught equals my 6 minus, let's see, what temperature are we doing here? Negative 20 degrees C. So that should be, what, 253 Kelvin times 0.022. Sorry, I ran out of space. So 253 times 0.022, that equals positive 0.5. Now, does that answer make sense? That it's positive 0.5, right? If we think about it, if we're at negative 20, is solid water going to change into liquid water? No, because we're below the freezing point, and so that's why it's going to be non-spontaneous. For letter E, on the other hand, though, for letter E, we're calculating delta G naught when the temperature is 20. And so for here, it's going to be 6.0 minus, and again, this one's going to be, instead of 253, it's going to be 293 times 0.022. And so that one gives us negative 0.45. And so in this one, it's spontaneous, right? So we have non-spontaneous and we have spontaneous, right? So we know solid to liquid doesn't happen below the freezing point, and it does happen above the freezing point. Crazy. Okay, so this is a cool problem. It's a cool thing to just kind of make sure that you understand what's actually going on when you're talking about delta G, delta H, and delta S. Yeah, don't black out, Mikey. That's not a good thing. All right, 79 and 93 were the other ones. What's 79? Did we do 70? Oh, we didn't do 79. I talked through 79 with a couple people. Yeah, we could do 79. Let's see. Do I want to do 93 first, since we're on challenge problems? Oh, 93 is fun. Sure, let's see if we can do 93. 75.3. Isaac's the first one to ask about the assignment sheet problems. Yeah, we can do that. Let's go ahead and do the last two from the text. Let's do 79 and 93. So I'll do 79 first. So 79... wait, hold on. What the difference in the way a reaction happens when it has a large... Oh, that's a tricky question that's a little complicated to explain. The magnitude of delta G doesn't really tell us a whole lot, except for it tells us we're at a temperature that is very spontaneous. But negative means spontaneous, positive means non-spontaneous. So... yeah, that's what I was afraid of, Lauren. Okay, so let's go ahead and look at 79. So we're talking about lead chloride. So we can write the process of lead chloride dissolving into lead ions and 2 chloride ions, right? And we want to know, can a 0.03 molar solution occur, right? In other words, can we fully dissolve 0.03 moles of this per liter? If we fully dissolve 0.03 moles of this per liter, our concentration of lead is going to be 0.03 molar, and our concentration of chloride is going to be 0.06 molar, right? You got to be careful of that too. And so if we start out with 0.03 moles per liter of the solid and we're trying to predict, is it going to fully dissolve, then the lead's going to be 0.03 and the chloride's going to be 0.06. Okay. So at 25 degrees C, what we need to do is we need to say, okay, let's see if we can find delta G from the equation. So I'm going to look in my chart on page 601, and I'm going to try to find the delta G of formations for these compounds. So if we swing over to 601, let's see, lead. All right, lead chloride solid is negative 314.1. Lead ions are negative 24.4. And the chloride ions are negative 131.2. Okay, so what we need to do now is we need to use these delta G formation values. We need to find the delta G of the reaction. So the delta G naught of the reaction is going to equal my products minus my reactants. So negative 24.4 plus, don't forget to multiply by 2 times negative 131.2, all of that minus a negative 314.1. So take out my calculator. So we get a positive 27.3. Now, so what this value tells us, because this is delta G naught, this tells us that if we're trying to make 1 molar solutions of each of these, that the reaction is very non-spontaneous. But the problem doesn't ask about 1 molar solution. The problem asks about 0.03 and 0.06. And so we have to recognize that we're not at standard conditions, and so we need to use the equation delta G equals delta G naught plus RT ln of Q. And so we actually need to solve for the value of delta G itself. And so let's plug in our values. 27.3 kilojoules per mole plus my R 0.00831 joules per mole Kelvin, or sorry, kilojoules per mole Kelvin, times my temperature, we're doing 25 degrees C, so 298 Kelvin, and then the natural log of, now I got to be careful how I do this, right, because we got to use Q, so we need 0.03 times 0.06 squared, right? Because the Q for this reaction is the concentration of chlorides squared times the concentration of lead. So we need to make sure when we plug in Q, it's 0.03, the lead, times the 0.06 squared. So again, this equation, Joel, this equation is when we're dealing with pressures and concentrations that are not 1 molar. And we had another version of this equation where we had a 0 for delta G and we plugged in K, and that was when we were at equilibrium. Okay, so now we just evaluate this. So we take 0.06, square it, times 0.03, take the natural log of that, times 298, times 0.00831. So I end up getting 27.3 minus 22.6. Which gives me 4.7. So yeah, pressure and concentrations is all that appears into Q. So delta G here, if we're using 0.03 and 0.06 molar at room temperature, 25 degrees C, the delta G is a positive 4.7. That means the reaction is non-spontaneous, and so you wouldn't be able to create a 0.03 and 0.06 molar solution at this temperature of lead chloride. So that's part A. Part B, on the other hand, asks, if the student uses water at 100 degrees C, would this be possible? And so in this, we're basically doing this whole equation again, but instead of plugging in 298, we're going to plug in 373. Okay, so it's literally the exact same as otherwise, except we just plug in 373. So let's do that and see what we get. So this time, I get 27.3 minus 28.3, which gives me negative 1 as my delta G. And so because delta G is negative 1, because delta G is negative 1, that means that the reaction is now going to be spontaneous. Right? So the fact that this solution cannot be prepared at room temperature, but it can be prepared at a higher temperature, just kind of is evidence, or is shown by the idea of just how our delta G here works based on temperature. Why A is not possible? Because delta G is positive. So because delta G is positive, the reaction with 0.03 and 0.06, the reaction is not going to go in the forward direction. It's going to go in the reverse direction. So because it's going to go in the reverse direction, that means that we can't sustain a 0.03 and 0.06 molar because delta G is positive. With delta G being negative, that means that we technically could dissolve more solid if we wanted to, and that the 0.03 and the 0.06 is fine. Yeah, it all comes back to this value of delta G. And this problem's a little tricky because you have to know what delta G means and how to apply it into an interesting situation. Okay, cool. So that was 79. And then let's do 93. Okay. Sorry, guys. If you can tell, I don't feel great. But I got the Rona. No, it should be okay. I've got a head cold. All right, 93. Ethyl alcohol, aka ethanol. We can abbreviate ethanol as ETOH. So ethanol, my delta H of vaporization. I don't know, Max. I think my kids were a little bit sick, so I think I just caught whatever they had. So delta H of vaporization equals 42.9 kilojoules. Kilojoules per mole. And then they tell us something interesting. They tell us that the vapor pressure, so the pressure of the gas equals 392 millimeters of mercury at 63 degrees C. Okay, and then they want us to find S naught. So what is S naught for my C2H5OH, aka ethanol gas? Okay, so what in the world, right? This problem just seems like those crazy math problems where they give you this random thing, this random thing, this random thing, and they ask you to find something that's totally unrelated. So let's see if we can find the connection between the information they gave us. So don't forget, delta H of vaporization corresponds with the reaction of C2H5OH liquid turning into C2H5OH gas. Okay, so we've got that. Now, this delta H of vaporization is for this reaction. So we know delta H. Okay. What else do we know? We know that the pressure of the vapor is 392 at 63 degrees C. Now, if that's the pressure of the vapor, that's the equilibrium pressure of the vapor. Okay? So K, right, because this is a liquid, K is just equal to the pressure of C2H5OH. And so what that means is because the pressure is this many millimeters of mercury, at 63 degrees C, that is K. And so K, we'll do it in atmospheres because K should be in atmospheres. Or I guess the pressures into K should always be in atmospheres. So let's divide that by 760. So 392 divided by 760, 0.516. So K equals 0.516 at 63 degrees C. Okay. Now, why do I care about K? Well, if I know K, I can solve for delta G, right? Because we know that delta G naught equals negative RT ln of K. So we can just plug in. So we get negative 0.00831. 831 or 813? How's my dyslexia? It's 831. Okay. All right. All right. Sammy, back to Sammy's good question, right? So can explain again why K equals the pressure. Okay. So remember vapor pressure. Vapor pressure is an equilibrium pressure, right? It's the pressure of the vapor. They're telling you that if you have a container with the liquid and the gas and you bring it to 63 degrees C, that the gas has a pressure of 392. That is the equilibrium pressure of the vapor. And so when we write K, K is our products divided by reactants, but we don't include liquids and solids. We only include gases. And so K equals the pressure of C2H5OH. If this had been a gas, right, then it would be this divided by that. But because this is a liquid, we don't include it. And so our K is just the pressure of this. If there had been a 2 here, right, it would be squared. But because there's just one of them, that's all it is. We just plug it in. Hopefully that helps, Sammy. All right, so 0.0831 kilojoules per mole Kelvin times temperature. We're 63 degrees C, which we got to change that to Kelvin. So 63 plus 273. So that's 336 Kelvin times the natural log of, and I'm out of room, 0.516. So let's plug that in. So 0.516 natural log times 336 times 0.00831. Right, so I get 1.85. A positive 1.85 kilojoules per mole. So that's delta G. Delta G is a positive 1.85. Okay, now that I know delta G naught, and I know delta H naught, I can find delta S. Okay, so we know that delta G naught equals delta H naught minus T delta S naught, right? We could rearrange this equation if we wanted. We could add T delta S, subtract delta H. If you rearrange the equation, I'm just going to skip through that. You get that delta H naught minus delta G naught divided by T equals delta S naught. So we plug in my delta H naught, 42.9 minus 1.85 divided by 336. 42.9 minus 1.85 divided by 336. So we get 0.122 kilojoules per mole Kelvin. Okay. Now, this is the delta S for the reaction. Okay. It's not the delta S for just the gas. Or sorry, it's not the S naught for just the gas. And so we probably have to look up the S value for C2H5OH would be my bet, because that's the only other way we're going to know the information for that. So if we look on page 601, I bet it's back there. C2H5OH, yep, it's right there. It's 0.1607. So if this is 0.1607, right? We don't know this, but we know the overall is 0.1222. I ran out of room. I'm just going to try to do this in this little box right here. Okay, so we know that products X minus reactants 0.1607 equals the total 0.122. And so X, which is my S naught, equals 0.223 kilojoules per mole Kelvin. Let's see if that's right. I'm going to be really disappointed if I'm wrong. 93.2827. What? What did I do? .2827. I'm close. Oh, because I literally can't add. Oh my gosh. 0.122 plus 0.16 is 0.283. Okay, so I'm good. I was right. I did all of this complicated math, and then I just can't add two numbers. Seriously, Isaac. Totally agree with that. Okay. Let's see. Assignment sheet problem next. Didn't we do... Oh, we didn't do 94. So Isaac really wants to do 75.1. Lauren, if we have time, we'll do 94. Let's look at 75.1. Wait, 75.1? I didn't even give you 75.1. You have 75.3, 84.3, and 90.3. Okay. So, so if you don't have your assignment sheet out, 75.3 gives you some interesting things, right? So it gives you this reaction, 2NO plus oxygen making 2NO2, and then it gives you the rate expression, right? This is just a fancy way to say rate. Rate equals K times NO2 squared times O2. So, throwback, right? So this is second order with respect to NO and first order with respect to O2. For the reaction above, find the rate constant at 25 degrees C if the initial rate, as defined by the equation above, is 28 moles per liter with a concentration of nitric acid as 0.2 and oxygen is 0.1. So all you're doing here is you're just plugging in and finding K. Oh, yeah. So yeah, Lauren, that's why we got some time to review. So let me pull this off screen. We'll come back to this in a second. Okay. So the idea is that, so this is 75.3. Rate equals K times the concentration of NO squared times O2. And so for A, you're just plugging in and solving for K. So K equals rate divided by NO squared times O2, which they told us the rate was 28 moles per liter second. Our NO concentration is 0.2 moles per liter squared, and our oxygen is 0.1. Okay, so then we just plug all that in. So it's going to be 28. So 28 divided by 0.2 divided by 0.2. It's going to be a big number. It's 7,000. Right? Now, 7,000 what? Remember, K has funky units. The K, the rate law K, not the equilibrium K, the rate law K. And so if we look at the units here, right, moles per liter cancels, but this one's squared. And so we end up getting, we have two molarities left over. And so it's molarity to the negative 2, S to the negative 1. Or you could say 7,000 liters squared per mole squared second. Yeah, everyone is remembering how terrible rate equations were. All right, so this is a good little reminder of how to calculate the rate law K. Okay, so let's go back. Let's look at part B now. Part B now asks, calculate the equilibrium constant for the reaction. Okay. So this problem's fun because they're asking you to find two different K's, and so you have to keep your rate constant K and your equilibrium constant K straight. And so this data for the delta H, the S naught, and the delta G's are what we're going to use to calculate K. We actually don't need the delta H of formations or the S naughts. We can just get away with using just the delta G of formations. Rates was, what chapter even was that? I don't even know. I'd have to look. It was at the start of, well, it was like halfway through second try. Okay, apparently it was chapter 11. All right, so let's use the data in the table. So we have our reaction where we have 2NO in equilibrium with, plus O2. In equilibrium with 2NO2. Okay, so we need to find delta G for the reaction. So the delta G values from the chart, the G of formations, were 86.7, 0, and 51.8. Okay, so we do products minus reactants. So 2 times 51.8 minus 2 times 86.7 plus 0. That's going to give us the delta G of the reaction. I get negative 69.8. kilojoules per mole. And then we can calculate K, because we know that delta G naught equals negative RT ln of K. And so to calculate K equals E to the delta G naught divided by the negative delta G naught over RT, right? That's divided by negative RT, take E to the power, and plug in. And so now we just plug in our values. So negative and negative cancel out. So it's E to the 69.8 divided by my 0.00831 times temperature, 25 degrees C, so 298. And that should give me K. Should be a big number. Oh, that's a big number. 1.74 times 10 to the 12th. Man, so many emails. Yeah, talk about a forward reaction. Let's see. Answers, double check. Yeah, 1.74 times 10 to the 12th. Yep. An overflow error. Logan, careful. Make sure that you put this 298 on the bottom and not on the top, right? If you type this in straight, sometimes it might take this 298 and shove it to the top rather than keeping it on the bottom. Make sure you do that in parentheses. Because, yeah, that would give you an overflow error if you tried to raise E to the, 900 power. Okay, I think that's it. Make sure to grade your homework. I'll post the review and test to Canvas so you guys can do that starting this afternoon. Yeah, that would give you an overflow error for sure, Isaac. So yeah, work on that tonight. If you need more help with the homework, just ask me in Discord this afternoon. I do have a meeting I have to digitally attend, but it shouldn't take too long, I hope. But I'll try to be in the Discord for most of the afternoon so you guys can ask questions. Feel free to tune into the Brighton Esports match versus Provo today. It'll be at 4 o'clock. I'll be streaming it. And, yeah. So there's a thing on Canvas. So if you go to Canvas, and go to the modules, there's a chapter 16 homework score thing. So you click that, download the PDF. It'll show you this is the answer key, right? And then you just, if you're a student here, you can submit it. Okay, bye, Isaac. Oh, yeah, I might be able to do 94 real quick, Sammy. KEQ, that's just the equilibrium constant K, Haley. It's just a general term for every K is KEQ technically. All right, 94. Delta HF for iodine gas. So we've got delta HF for I2 gas equals 94. 62.4 kilojoules per mole. S is 260.7. kilojoules per mole Kelvin. Calculate the equilibrium partial pressures of iodine, hydrogen, and HI. So we have 2HI gas in equilibrium with H2 gas plus I2 gas. Calculate at 500 degrees C. You're going to have to do an ice table to do this, as a little side note, if you guys didn't pick that up. If the initial pressures are all 0.2 atmospheres. Okay, so what you can do is you can use the delta H and the S values to calculate delta G. Then from that delta G, you can calculate K, and from that K, you can make an ice table and find the equilibrium concentrations. Okay, so we know before we do this ice table, we need to calculate K. In order to do that, we need to look up the delta H's and S's of all the things. Okay. Don't forget your sig figs, Braden 1821, with a whole bunch of lulls. Sure. Okay, so we need to look up the values from the chart in the back of the book. So HI is 26.5 and 0.2065. Hydrogen gas is 0 and 0.1306. And then iodine is 62.4 and 0.2607 if we want it to be in the proper units. Okay, so then we need to find the delta H of the reaction overall. It's going to be 0 plus 62.4 minus 2 times 26.5. And then the delta S of the reaction is going to be 0.1306 plus 0.2607 minus 0.2065 times 2. So we get 9.4 for the delta H of the reaction, kilojoules per mole, and we get 0.0217 kilojoules per mole Kelvin for the delta S. Okay. So then now we can find delta G of the reaction. So delta G naught equals the 9.4 kilojoules per mole minus my temperature, which is going to be 773 Kelvin. Because we're at 500 degrees C, we need to do 773 Kelvin times my delta S, which is a negative 0.0217 kilojoules per mole Kelvin. So my overall is 26.2 as my delta G. Kilojoules per mole. Okay, so now that we have delta G, I'm going to need another page to do this problem. Now that we have delta G, we can find K. Okay, so we take delta G naught and we can find K using our other equations. So I'm just going to... So we know that delta G naught equals negative RT ln of K, or K simply equals E raised to the negative delta G naught over RT, which in this case is going to be e raised to the power of negative 26.2 over 0.00831 times 773. So my k equals 0.0170. Okay, so a pretty small k. So if we go back to our reaction, right? Just use parentheses, Logan. You can handle it. It might help to evaluate this first and then just do e to the power. Okay, so if they're all equal to each other, the k is less than 1. That means it's going to be reactant favored, so we know it's going to shift to the left. So in our ice table, point 2, 0.2, 0.2. We know this side's going to be plus 2x, this side's going to be minus x, this side's going to be minus x. And so my equilibrium is 0.200 plus 2x, 0.200 minus x, and 0.200 minus x. Now, we can't get rid of any of the x's, and so my k, 0.0170, equals 0.200 minus x quantity squared, because it's this times this, divided by 0.200 plus 2x quantity squared. So that's our products multiplied by each other divided by the reactants equals a k. We're going to square root both sides because that way we don't have to solve a quadratic. So we get 0.130 equals 0.200 minus x divided by 0.200 plus 2x. Multiply across, so times 0.0261, so 0.0261 plus 0.26x equals 0.200 minus x. Let's add x, subtract 0.0261. We get 1.26x equals 0.1739. Divide by 1.26, x equals 0.138. Plug back into the ice table. The pressure of H2 is the same as the pressure of I2, which is going to be 0.062. And the pressure of HI is going to be 0.467 or 0.476. No, Lauren, I don't know how you would eliminate those. That doesn't work. That would only work if your K was very large. Like this is going back to like the chapter 12 stuff where you can't actually eliminate the x's. So the reason why this problem is a challenge problem is because they took an annoying problem from this chapter and combined it with an annoying problem from 2 or 3 chapters ago, and so it takes 2 whole pages to do. Okay, because what you had to do is you had to use the delta H and the S from this equation. You had to find the delta H of the reaction, find the S of the reaction, find the delta G of the reaction, use the delta G of the reaction to find the K of the reaction, use the K of the reaction in an ice table, and not just a simple ice table. In an ice table, you actually have to evaluate algebraically, get the value of X for the change in your ice table, and then plug that back into the equilibrium concentrations. Yay. Okay, so this problem was a beast. I guess it's probably a good thing I did it for you, or helped you through it. If you have any other questions, of course, show up in the Discord at noon. I'll be there from, I think my meeting's at 1:30. So from like noon to 1:30, I'll be in there, and then maybe a little after that if my meeting finishes. You are welcome. Otherwise, good luck finishing the homework. Get the homework score reported. I'll upload the review and the test, hopefully this afternoon, maybe tomorrow morning. And then we'll go from there. So, good luck. Come to the Discord if you have more questions. And probably not tonight, Max. It'll earliest it'll be tomorrow. All right. Bye.